Hello everyone. This week we're going to talk about dimensionality reduction. It is the third stage in the data mining model, the 10-step data mining model that is described in the first part of our textbook. And we're not going to dig into it as deep as the chapter goes into, just because that's more than probably we need to go into. I will talk to you about principal components analysis at the end, but I'm not going to actually go through the code that they go through to show you how it works. But anyway, essentially, backing up a bit, dimensionality reduction is really used when we have too much data. And there's a lot of data there, and some of it maybe is very similar, or some of it is useless, or some of it represents kind of a relationship to another set of data points. And so we're going to reduce the amount of data that we have, and we're going to reduce the dimensions. This becomes an issue when, one, there's a huge data set or large data sets, and we want to actually reduce the dimensionality of it simply because it's easier to process given the computer power that we have, or when you're using algorithms for which you have to account for all of the dimensions in the data, and that becomes complex, probably exponentially complex as you add more dimensions. So by reducing dimensionality, we're actually reducing complexity and making our work much easier. We're going to build a little bit on what we talked about last week with the plots. I'm going to actually use a couple of histograms in this presentation just because I want you guys to feel sort of like more comfortable using those plots to sort of learn things about your data set and learn things about what the data are telling you. And then the Boston housing data, which is what we're going to use, actually some of the tools that we use, we start to find problems in the data set, and problems that we will actually have to account for, because there are outliers, that one of which is probably a mistake and the other one of which is probably a true outlier and could be explained away, but it just needs to sort of make sense. So anyway, here we go. So now that we've looked at our plots, we're going to consider the issue of dimensionality. And dimensionality is basically the more fields we have, the more dimensions we have. The more dimensions we have, the more complexity that we have. And so this could actually, dimensionality reduction can pay off in a number of different ways. The easiest one of which I've already mentioned, that is, you cut out some of the data that you don't need. And if you're not dealing with a huge set of, or if you are dealing with a huge set of data and you make it less huge, then it's easier for you to be able to actually work your way through it. But also, it gets more complex than that, in the sense that every dimension that you add adds levels of complexity to certain processing steps and certain algorithms, and that slows them down, or can add error, or can add other sort of unexpected results. So the dimensionality reduction can really help us with that. So let's look for ways to trim the data down. So we've got the housing data again. So I'm going to go ahead and cut over to R, and we'll go ahead and load that data up. And they've called it something different this time, which is a little curious, but I will go ahead and follow their convention so that we're the same as in the textbook. But it's Boston, Boston.housing.df, set that equal to the results of read.csv. And we load our data set. Okay, there it is. And I can do a view command to look at it, but didn't throw me an error message, so I'm pretty happy that it's in there. Okay, let's go back. So what's some of the first things that we can do? Now, we've talked about these before, and I'm going to talk about them again. And I think maybe, if we go through some of these steps a couple of times, you'll start to see the usefulness of them. But there are a couple of things we can do with this data set. We can do a summary command. And a summary command is going to give us basically a range, a mean, a median, and it's going to give us sort of the 25th percentile and the 75th percentile for every one of the numeric values that are in the data set. So that's just an overall summary, and that's actually pretty nice. There's also mean, standard deviation, min, minimum value, max, maximum value, median value, and then length. So each one of these we're going to use, but we're going to use them a little differently, because those commands are actually intended to be used with a single variable. So we can use mean for a single variable, like for example, we can use it for the crime rate, or the percentage of crime, or the percentage of lower status, or something like that, that is one of the 14 fields in our file. But I will show you a way that they actually use it across all of the different data points. And the same goes with standard deviation, min, max, median, and length. So we're going to go back over to R, and we'll see these in action. And I have actually created a script. So I'm going to load up the script, open my script. My script is called, I've got to find it, dimensionality. All right. So just like we did last week, this week I built a script, and I've already done the first step, and that was to load the data. So that's already in there. The next step is to actually run the summary command. So I'm going to put my cursor next to the comment, hit that, it will run the comment. Actually, I'll reduce this so we can see what's going on, and move this screen over here. And then the next command is to get my summary statistics, and that's exactly what it did for all of the fields in the file, starting with crime rate, zone, industrial land, proximity to the river. It gave me the minimum value. It gave me the first quartile, which is everything above that is, or there's 75% of the points are above that, and 25% of the points that are below that. The median is the middle value. The mean is the average. The third quartile is 75%. Everything above it is 25%, and 75% of the points are below it. And then your maximum value, which is 88.97. And that is just for this particular field. There are 14 fields in this file, so it gave us those variables, those values for each one of those 14 fields. What's curious about this is that when you come to a categorical variable like Chaz, which is for the Charles River proximity, you'll notice that there's either 1 or 0. So it does this summary and it does all that other stuff, but it's really a categorical numerical variable, and it doesn't make a lot of sense. Your maximum value is 1, your minimum value is 0, and your first quartile and your third quartile and all that other stuff just doesn't really work. So you'll see that sometimes the summary command isn't really going to work that well with certain fields in the file. So let's go ahead and look at this particular variable. This is the crime rate for each of the neighborhoods. Now, remember, the records in this file, there are 506 records, and they represent certain statistics about 506 different neighborhoods in the Boston area. So what we're looking at here is we're looking at the crime rate associated with each of those 506 neighborhoods. What we're going to do here is we're going to run a mean, standard deviation, min, max, median, and length. And we're going to go ahead and see what each of these returns to us. Okay, so we'll go ahead and go back over to our script. Come down to our comment, just tells us what we're doing. And then we're going to go ahead, what's the mean? The mean gives us a singular value, 3.615 or 3524. That is the mean crime rate for all of those 506 variables. Next is our standard deviation. That's a pretty high standard deviation considering that what the mean is, which that seems to suggest that if you've got a high standard deviation, you've got a fairly wide scatter around the mean, which means amongst those 506 neighborhoods, the crime rate varies quite a bit. The next value, my minimum value, which is almost no crime at all. After that is followed by my maximum value, which is a really high crime rate, which I kind of have to question. I kind of have to wonder, is there really a neighborhood out there that has an 88.9762 crime rate? Maybe we have to look at how we're calculating that, and maybe we have to look at whether or not that's actually valid data. Median is 0.25651. And the length, which is kind of useless in this example, is 506. Actually, it's not going to work. I don't know why. There's a problem with it. Worked before, but I'm not going to worry about it right now. It's because it's spelled wrong. That's why. Anyway, it would give you 506. And giving you 506 is just basically that's the number of records that are actually accounted for in that field. They're all going to give you 506. The nice thing about the length one is that if there's any data that are missing, then the length command will return a number less than 506. And you can understand that you've got some fields in that particular variable that are blank. All right, so what is this telling us now? Now that we've got this data for the crime variable, it'd be kind of nice to have this for all of them. Well, there's a nice little command that they have, and I'll explain it to you. Let's see if I do it in the actual PowerPoint. Let's go to the PowerPoint. Okay, let's go back a little bit. Let's go back to what did we learn? So we looked at the crime variable, and we looked at the mean and the median both, and we saw that the mean, go back to this, the mean was 3.613524. The median, however, was 0.25651. That seems to suggest that your middle value is lower than your mean. When you have a big difference like that, where the middle value is lower than the mean, that means that you've got some high values over on the right-hand side. It's known as what's being right skewed. And so this is pulling your average up. Your average is being pulled up to many times higher than the median, than the middle value, simply because you've got some neighborhoods there where there's values that are kind of off the charts high. That gives you information about what to do, about whether or not you look at those high values and you say, those are outliers, and they're pulling my average up, and they're artificial, and I'm not going to really need them that much, so I can eliminate those, or I can set those back to, a lot of times, one of the strategies that people use is to take those giant outliers and they set them to the mean. So they can, or they set them to the median, or something, that is a little lower, but something that you can justify. So that's what we'll see when we looked at that with the right skew. What else do we know about this data? Again, we're looking for extremely high values or extremely low values. Our length command, like I said, will give us some indicator that we've got any missing data. Let's actually look at this visually using histograms. We'll go back to our script. Before we get to the histograms, I'm going to actually show you the command that they use in the book that allows you to see all of the data at the same time in a similar table. And so this is actually using some commands that we've not seen yet. We're setting a data frame. The mean in this data frame is going to use a command called sapply, which is basically universally apply this to all values that are in the data set that are in the mean column. And then call that column mean. And then we're going to do the same thing. We're going to put in the standard deviation is going to be set equal to sort of universally apply the standard deviation command to the Boston housing data standard deviation column. And then we're going to keep going through all the way through all of our commands, and we'll run each of these commands on the entire data set. Getting to the end where we're running our length command. Our length command is a little different. The length command it's also an sapply, which is universal apply. We're going to apply that to the data that's in the data frame that we've created. And what we're going to do is we're actually going to run length on it. Then we're going to see how many of them are empty. And we use the miss.val is set equal to an sapply where housing.data.df is our data frame. And we have a function x, and the function x gets populated by us doing the sum length where there's basically nothing in x is what this command is doing. Give us the number where there's basically nothing in x, drop that into function x, and drop that back into this value. And it'll give you any of them that are missing data. So again, this data frame command, we're going to run mean, we're going to run standard deviation, we're going to run min, max, median, and all those commands across the entire data set, and we're going to build a data frame called data frame actually, and it will just go ahead and display it for us. So we'll go ahead and run that now. And it gives us this data frame. Okay, so here are our 14 variables. Here are the columns that we created when we ran this command. We have mean, we have standard deviation, we have min, we have max, we have median, we have length, and there are none of them that are missing values. Okay. Well, go back to crime for a second. If we look at crime, we see that the mean is 3.613, etc. And the standard deviation, we've got that there. But we also have the median. Remember I said the median is a lot smaller, which means that this is basically being pulled up because you have values over on the right-hand side. There doesn't have to be very many of them, but they're values on the right-hand side of your distribution that are so high that it's pulling your mean up. Same thing can be said of the zone. That's looking like it's set up that way too. The industry is a little bit higher. It's not such a distribution, not such a right skew distribution. And if you look at the average number of rooms per homes in the neighborhood, you've got 6.28 is your mean, and over here your median is 6.20. Let's take a look at three histograms, one of which shows right skew, the other one shows sort of an uneven distribution, and the third one shows pretty much a natural even distribution. And we can do that by going through our histogram. So we're going to use a histogram command, the simplest one. We didn't have to download or load any libraries to do this. We'll just do a simple histogram command of the crime variable, and this is what we get. So most of the neighborhoods, remember there's 506 records in here that have values for crime rate. And most of those fall in between, in this first bucket here, between 0 and what looks like 10. Then you've got some that fall between 10 and 20, then a few of them that fall between 20 and 30. But you've got a very small number of very high crime rates. And to me, this is a right skew. This is clearly a right skew because you're skewing off to the right. It's pulling the average up. And to me, it's indicative of there being erroneous data on the far right side. It is unusual that you would find neighborhoods that had 40, 60, or 80% crime rates. So I'm thinking that there's a problem there, and we've got to correct that. So our job then would be to load up the data file into something where we could actually run a command and either blank out those high crime rates because they're just not right, or set them to something, kind of project something that is more of a reality that could be like the mean or something like that. But anyway, that's what that right skew is showing you. The next command is a histogram of distribution of industry. And this one's a little weird because it's showing the percentage of land that is actually non-retail land, non-retail, non-residential. And it's a pretty even distribution until you get to this bar here, between just under 20. Somehow there's a lot of neighborhoods that have 150 neighborhoods. Is that right? Again, it could be. It could be right. It could be that there's just that many neighborhoods that have that level of non-industrial, non-retail, or non-retail, non-residential land. But probably not. That's probably an error. And we're probably going to want to go in and figure out what that looks like and see where that came from. Anyway, it's something to be suspect of because it does look a little weird. The next histogram we're going to run is going to compare the number of rooms. Okay, the average number of rooms per house per neighborhood. The mean and median are very close in this one, and that looks like a fairly normal distribution. We're looking for that bell-shaped curve where your mean and your median are looking pretty close. So that one I'm probably thinking is looking okay. I don't see anything that's wrong with it. Nothing jumps out at me. Unlike the first two, the first one where we had the far right skew, and the second one where we had that big bubble there kind of towards the right that looked like it might have been out of place. But that's the power of histogram. What histogram can show you on a field-by-field basis, it can show you the distribution of these fields. And you can start looking at them and saying, wait a minute, does this make sense? Is this good data? Or is there one or two really high values that are pulling this off the charts and making it look like it's not right? And what do I need to do to go in and correct it? All right. So there's a couple other commands that I think are very useful for us to sort of get a feel for what's in the different fields in our data set and get a feel for what's in our data set overall. And one of them is called table. Table is a really cool command because what it does is it will take a categorical variable and it will count all of the things that match that categorical variable. So if you have, for example, when we did the Charles River proximity, we had a whole bunch of zeros and a whole bunch of ones. If we do a table, and I think we did last time, but if we do a table on that particular field, it will break down all of the categories that match 0 and all the categories that match 1, and it will give us a count. So table works really well for categorical variables. It doesn't work, or categorical, even numerical variables. It doesn't work very well for continuous numerical variables because you're going to get 1 in each spot. So we may have to modify the data first before we run table on it. Before we get there, let's just go ahead and repeat what we did last time, which was to run kind of a table on the proximity of the distribution to the Charles River. And it gives us, of the ones that are set to 0, meaning you're not close to the river, 471 are set to 0. There's 35 that are set to 1, which means 35 of them were close to the river. That's pretty convenient and pretty nice. Pretty good way of counting that. Well, the next thing we're going to do is we're going to do something that is going to allow us to take those data points. In fact, it's going to take more than just the Charles River data point, and it's going to allow us to sort of aggregate those into buckets that we can then look at. And once you start getting a feel for this, you'll realize that this is really powerful because we can start taking categorical variables and we can start calculating non-categorical variables based on their fit in the categories. So let's go back to our PowerPoint. Okay, we're looking at this aggregate command, and it's going to combine values and build a data frame and show the results. So the first thing we're going to do is we're going to combine values. There are many ways that we can do this. We already saw this last time with the Charles River proximity, where we combined all of the median values for those that were close to the river and all of the median values for those that were not close to the river. And then we ran a section, or I ran a command that allowed us to okay, sorry, I slightly interrupted there. My battery went out, but it's back. Okay, as I was saying, we looked at this before with proximity to the Charles River,
And we broke apart all of the median values for those that were close to the river and those that were not close to the river, and we put them into separate buckets. Once they're in separate buckets and they're separated out, that allows us to do whatever we want with them. We can summarize them, we can average them, we can do whatever we want. There's a command called bincode, .bincode. And what .bincode does is a different way of being able to allows us a different way of being able to sort of break things into bins. It's, if you think about a histogram presents things in bins, and it gives you a count of the number of things that fall into each of those bins. Bincode does something similar. What it will do is it will take a field and it will break that field into bins, and you can feed it what you want the bins to be. So if we were to take the variable RM, which represents average rooms, we can see in our data set and our summary command that the range runs from 3.561 to 8.780. So if we want to know what is the median value, the average median value per room, or based on the number of rooms, I should say, this is a command that will allow us to do that. So what we're going to do is we're going to break those 506 values into bins that range from 1 to 9. And that 1 to 9 is going to represent the number of rooms that are associated with each of the houses. Now, the problem is that the number of rooms associated with each of the houses isn't really associated with houses. It's an average number of rooms for that particular neighborhood. So because it's an average number of rooms for that particular neighborhood, it's taken out to several digits, several decimal places past, several places past the decimal. And that makes it really hard for us to treat it as a categorical variable because it is continuous. So what we're going to do is we're going to use the bincode command, and we're going to drop them into bins based on their average, and they will be dropped into the bin that most closely represents their value. Okay.
So here's the example. We have the Boston housing data. So bostonhousing.df, that's the data frame that we created, and we're isolating out the RM variable, and we're calling it something different. We're calling it rm.bin. So it's creating actually a new variable for us, putting it into our data set. And what we're going to do is we're going to populate that variable for all 506 records with the bin code value for the Boston housing data variable room, or average number of rooms, and we're going to feed it a vector of 1 to 9. So what bincode is going to do is it's going to strip off those decimal places, and it's going to take the integer that's left, the one that is to the left side of the decimal, and it's going to drop that value into rm.bin for each of the 506 records that we have. Okay. And what that does is it allows us to sort of take a continuous value, like average number of rooms, and turn it into a categorical variable. That gives us a lot of power, because now what we can do is we can use the aggregate command to categorize all those that dropped into 3, all those that dropped into 4, all those that dropped into 5, and now we can isolate those out, and we can calculate what the median value, or the average median value, I should say, is for each of those different categories. That's very helpful. What's also nice about this is that we can, when we get to the aggregate command, we can now look at not just one variable like we did with the proximity to the Charles River, but we can look at two variables at the same time. So we can look at what is the average median value for a house that has 4 bedrooms that is close to the Charles River, and what is the average median value for a house that has 4 bedrooms that is not close to the Charles River, and how do they compare? The first thing we'll do is we'll worry about this binning, this bin code. This basically is going to add a field to our data, so it'll be the 15th field. It's going to call it rm.bin. It's going to populate it with whatever category bin code assigns for each of our average room values, be a single integer digit, and it will populate that file. All right, here is our command, our bin code command. So we'll go ahead and move through that. Okay, it is done. We don't really see it, but it's done. Okay, the next thing we're going to do is we're going to compute the average of the median value by our binned RM room codes and by our proximity to the Charles River. Remember, that's 1 and 0. So now they're both categorical variables. This one happens to go 3 through 8 because there's no houses that are only 1 room or 2 rooms, and there's nothing over 8. And then the Charles River is 0 and 1. So we'll be able to build a table that actually looks at these two things separately and combines them. So we'll be able to look at 3 rooms close to the Charles River, 3 rooms not close to the Charles River, and so on. And that is done through our aggregate command. With aggregate, what we're doing is we're saying, take this data and take this field, which is my median value, and aggregate it, but do it by two variables. The first thing you're going to do it by is you're going to do it by my bin variable, my RM bin, the one I just created. It runs 3 through 8 for every one of my 506 records. Okay. Then look at my proximity to the Charles River. Okay, and break it into a two-dimensional matrix and show me what the numbers look like. Okay. The last thing it's going to do is, because I pulled in this median value, it's kind of hanging out there, right? And it's got a bucket of houses that the bin is 4, and the proximity to the Charles River is that it's close. There's some number of those, and they all have median values. So what am I going to do with that median value? I'm going to actually calculate the mean of that median value. So this single command will give me the table of median values broken out by my two variables. All right, let's go ahead and run that. And there it is. Rooms are represented here. Proximity to the Charles River is represented here. The mean median value is represented here. And you'll see that I have a category where there are 3 rooms. It is not close to the Charles River. Category 4 rooms, not close. 5 rooms, not close. All the way up to 8 rooms, not close. Well, ironically, though, we do not have any records where there are 3 or 4 rooms that are actually close to the Charles River. We start at 5. So 5 rooms close to the Charles River, 6 close, 7 close, 8 close. And that's the end of our data set. It's binned our data, separated it out by the Charles River proximity, and calculated an average median value across each one of them. Okay? Something looks funny. There are some problems. And we knew there was going to be problems because that's the way it was probably set up. All right. Let's take a look at the data and see what looks funny here. We're looking at our smallest houses, 3-room houses. They are not close to the Charles River, so they lose that perk. This is by the record number 1. It has a median value of 25,300 or 25,300. The very next category up, which has 1 more room and is also not close to the Charles River, is full $10,000 lower. The very next category up is still $8,000 lower. Category after that is $6,000. And you don't actually catch up until you've got 7 rooms. So something's wrong here. Something's wrong with the data set here because you've got 25,000, which just doesn't match the progression that you're seeing with the rest of the categories. It would make sense that you would have a correlation between the number of rooms and the price, the average median price of the house. But the first category doesn't look right.
So we have to go back to our data and look at what's wrong there. Well, it turns out you've got two records of the 506 where the average number of rooms is 3. Both of them are not close to the Charles River, and they have a really high value. Unless there's something really special about those homes, I'm going to categorize that as erroneous data and realize something's got to be done. We're going to have to fix that data. So,
2 small houses far from the river, probably outliers, probably not useful for our analysis. We probably are justified in dropping them off out of the data set. And you always want to be careful about dropping things out of a data set because you don't want to do it to introduce your own personal bias. So when you're dropping something, making a decision to drop something out of a data set, if you can't come up with any reason why those 2 small houses would be worth more than houses that had several more rooms, that's probably an outlier, probably a mistake, and you're probably justified in dropping it. On the other side, we have something that is kind of silly as well, and that is that we have houses. These are houses that are close to the river. The 6-room houses, 25,918. 7-room houses are 44,06667, and the 8-room houses are 35,950. So this deserves to be dug into a little bit more. So if you look out at the data set, you see that 6 out of 45 7-room homes that are close to the Charles River are actually kind of high priced. They're kind of up in that range. Only 2 out of 11 are actually close to the river, and so those are higher priced. From a percentage standpoint, they're about the same. I don't know that you could find justification for throwing out the data for the 7 rooms. It isn't that far off the charts, and it could be that there's just 1 or 2 of them that are much higher in median value. But it deserves to be looked at and see if is it a couple of them that are kind of pulling the value up, or is it something else that's going on here? Is there a single house that is like, suddenly it's $105,000 and it's pulling everything up? That's probably an error. But if you got, that
difference distributed across the 7 houses, or I'm sorry, the 6 houses, then it may not be an error at all. But anyway, it's good. It just illustrates that it's worth looking at. So we did a quick distribution, and this is how I found out. I used the table command. Now, before we used the table command on a single variable, but you can use the table command on multiple variables. So in this particular case, we looked at room.bin, and we also looked at proximity to the Charles River, the Chaz variable, and it gives us a 2-dimensional table, and it shows us that for those that are not close to the river, 2 of them have 3 bedrooms. 6 of them are close to the river that have 7 bedrooms out of 45, yet we know that that value is much higher. And only 2 out of 11, or 2 against 11, 2 out of 13 total, are with 8 rooms and are lower. So anyway, it just gives us kind of a breakdown of what those values are. Now what we're going to do is we're going to look at one more thing, and that's going to be to take a look at correlations. We're starting to think about this idea of what could we potentially eliminate. So we've looked at the data, kind of like we looked at the data last week with plots and got some idea of how things were looking with plots. Now we dug a little deeper and we looked at some of the numeric values using things like table and aggregate and the like to find out how does this data really look, and how does this data look across certain variables that we really might be interested in. Now what we're going to do is we're going to try to see if there's an opportunity for us to take a look at this data set and say, okay, imagine that it was 506,000 or 5 million records, and a couple of my fields have correlations on the order of 0.7 or 0.8, which means that when one variable goes up, the other one goes up pretty much consistently in the same manner. That's an opportunity for me to be able to get rid of some fields because I don't have to add that level of dimensionality when I don't need it anymore. So we're going to go ahead and run a correlation, basically a full correlation of the entire data set. It's going to check every variable against every other variable and give me a feel for any of them that might actually look like they're pretty highly correlated. All right, I'm going to go ahead and expand this, minimize this, and expand this one. What is this telling me? Okay, well, first things first, I'm comparing crime to crime. That's going to have a 1.0. Correlation because you're comparing one thing to itself, and that's meaningless. So, but we'll know that we'll have that for every single variable across our entire table. What I'm looking for here is I'm looking for things that have a pretty high positive or pretty high negative value that seems to indicate to me that there might be some level of correlation that I could take advantage of. Here's one, 0.63. So that's 2 variables that are looking kind of high. Tax rates. Tax rate is correlated to crime rate. That might be something I could take advantage of. They're kind of mid-range though, so I'm not really thinking that there's a whole lot here that I'm going to use. Let's look at crime rate versus industry. Well, that's 0.41. Not too much there either. So as I look through this entire data set, I'm not seeing too much that's jumping out at me. There is one exception, and one exception, I see a 0.92. Look at that, 0.92. That might be something that I really want to look at, but uh-oh. The problem is that it is comparing the average room size to the bins that I created for average room size. Guess what? One is basically derived from the other, not a useful comparison, so it's not terribly useful for what I need. I can look at some of these others. Now, these are just a carryover of the remaining variables that didn't fit on the first row. But I can look at crime for the percentage of people who are in lower economic status, the amount of non-residential, non-retail property is got a 0.6 correlation to crime rate. So I can look through these values. I'll tell you right now, nothing really jumps out here. There's a negative 0.74 between median value and lower status. That makes sense. That might be something that's actionable simply because you have something that is fairly highly correlated. This one is the number of rooms and median value. That makes sense too. People are going to pay more for houses that have more rooms. So there's nothing really jumping out. But anyway, this is the way that you can look at a data set, round it. And by the way, our command was basically to round the correlation of every field against every field down to 2 places. And that's what it gave us. Again, nothing really jumping out at us, but it does give us an idea of what it is we actually have in our data set. Okay, so one last thing I want to talk about, and that is principal components analysis. The chapter that we're working on this week concludes with principal components analysis. And I'm just not going to go into the level of detail that the book goes into, but I will take some time to explain it to you and what it means. What we're doing with principal components analysis is we are taking a data set, and it could be our housing data set, and it could be the 506 records across the 14 fields. And we are trying to account for variability across different fields in the data set. Instead of having 506 times 14 different variables, is there a way that we can actually identify a single representation of some percentage of that data? In other words, what if there was 100 records in our data set and we were really interested in median value, number of rooms, and crime rate? And those 100 records all looked really similar across those three variables. Instead of having 100 records, we could reduce that down to our principal component and have a single principal component that represented those 100 records. Then we would go on and search for another comparison. So we might then find 50 or 60 records, say, that had similar values to each other, but were very different from the first principal component. So the first principal component is standing there kind of by himself, and the second one, very different from the first one, is made up of all of those records who are similar amongst themselves. So you get the idea that what we're doing is we're basically creating these principal components that come in with a weighted representation of the different variabilities amongst our data set. And it's within certain measurements that we would do this. When we came up with our data, for our first principal component was 100 records, so it might account for 100. And the next one was made up of 60 records, so its weight might be 60. And we would keep going and calculating principal components until we got typically to about 85 to 90% of the variation. Once you get past that level, 80 to 85 to 90% of the variation, your principal components are so small and made up of so few records that you might as well just use the records that remain anyway. So when would we ever use this? So imagine that you had a data set that was just enormous. And a good example is, the number of people that travel, the number of people that are going to fly today. There'll be over 1 million people that fly today. So what if we wanted to do some data analysis of that, the data that has to do with that 1 million people that are flying today? That's 1 million records. And it could be even more than that. Maybe we're doing it for an entire week. So we could be looking at 7 to 10 million records, just the people flying in the United States. That's a huge data set, but for some reason we need to know information about that. So we can start looking at the fields that we are gathering about all of those passengers that flew on all of those flights over the course of the week and see which fields are meaningful. It could be things like the number of miles flown, the amount of fare paid, whether or not they were domestic or international, which would be a categorical variable, and the frequency of the travel. Is the traveler, somebody who is a gold status traveler on a particular airline, or are they just onesie-twosie kind of a year traveler? These all could be things that were very helpful for us to know. And it could be helpful in the way that it's for marketing, because we want to be able to market to certain people who are frequent travelers, but could also be helpful in the sense that we are trying to track unusual behavior amongst passengers for safety reasons. So we could take anywhere from 7 to 10 million records and start kind of looking at them, comparing them across that huge number of records, and come up with, for these 4 different variables, we come up with multiple different components that represent certain behaviors, certain categories of behaviors. So the first component could represent, somebody who flies a lot of miles, pays a lot of fare, they're going international, and the frequency of travel is very high. That could be one component that represents 15% of the variability in our data set. And we continue to come up with principal components that would represent different combinations of those 4 variables, keeping in mind that each principal component would be it would be not correlated at all to any of the other principal components. That's the whole point of principal component analysis, is you're coming up with categories of records that are entirely different from every other category of records. When you get to about 80 to 85%, maybe 90% of the variability that is accounted for across those 4 fields, you'd stop. And you basically say, I've got these principal components. I've reduced my dimensionality now from, say, as high as 10 million records, maybe down to some number that is a fraction of that, because you're able to use principal components instead of millions of records, because the principal components that are weighted, so we don't lose the number of records that they represent, but a single principal component can stand in for hundreds of thousands, if not millions of records. So anyway, that's principal components in a nutshell. You're welcome to read more about it in the book if you like. There's also videos out on YouTube about principal components analysis. You're welcome to look at those if you want. Some of them dig pretty deep into the statistical background of principal components analysis. I didn't want to go into that much. That's why I wanted to just give you sort of an overview of it. But it will at least give you an idea. And there's, bits of little nuggets of good information in each one of those. All right, so to summarize, what was this all about? So last week we looked at plots and summaries. And this week we looked a little bit at summary statistics, and we looked at some plots. So what we're trying to find out is if the data are meaningful or useful. Okay, Boston housing data, was it meaningful or useful? We looked at the data to find out what problems we might have identified, and we just got started. We actually just started scratching the surface because we really looked at a couple of the fields. But they may have been the fields that were the most important to us, and we may choose not to look any further beyond them. And there may be some actions we need to take before we can feel like the results that we get from processing this data or using this data are going to be useful for us. So we may have some fields that we need to correct for. What are we going to do about those two neighborhoods that the average number of houses is 3, but the price, the average and the median value is really high? Something's wrong there. It's either the number of rooms or it's the median value. And then we need to look at that one example where we saw that the median price for the rooms that had 7 houses that were close to the river was a little high. It looked a little high. And then there was the other examples. And we don't want to be off. We want to be as accurate as possible. So that's why we're going to correct our data. And we're only going to delete data when we feel like we have a really justifiable reason for doing so. If we can't correct the data, then we can delete the data. And then we could, use different, there's functions out there that will allow us, like principal components and other similar data reduction algorithms will allow us to sort of take millions and millions of records and reduce them down to some smaller dimension that will allow us to be able to work with them. So remember, when we're dealing with 506 records, it's not really that big of a deal. So what? We have 2 records that are off at the lower end for the number of rooms. We can deal with that, right? But when we're dealing with 500,000 or 5 million records or 10 million records, as in the example I gave you for the air travelers, it becomes a big deal. And then it really can stop up your algorithm, stop up your data mining, and mess up your results. So we're going to talk more about this. I will give you your exercise as a separate activity for you, and let me know if you have any questions as you work through that.